there's any questions that you still have concerning those, please let me know. I'm just going to go through the pages really quickly. This is chapter 7. Here we go. So we talked about physical states, solvent, solute, and solution, and classifying each as a solution and non-solution. We talked about miscible and immiscible. Remember, miscible is mixable, soluble and insoluble, saturated, unsaturated, and supersaturated. We talked about the terms that would be used when meaning saturated, unsaturated, and supersaturated. We found solubility, and we're able to tell that. We were able to look at a graph and figure out what the solubility of salt was from the graph. We were able to take and then describe things as miscible or immiscible to be able to draw a cation and anion as a hydrated ion. We were able to look at the things that would help increase the rate of dissolving. We talked about exothermic and endothermic. We talked about being able to determine if something was soluble in something else because like dissolves like, and so if it was polar, it would dissolve a polar thing. If it was nonpolar, it dissolved nonpolar. We talked about molarity, moles divided by liters. Remember, it's moles of solute divided by liters of solution. We actually calculated molarity several different ways. We calculated moles and we calculated liters. We then calculated grams. We talked about percent. We talked about pph, ppm, ppb, and then weight percent, weight volume percent, and volume percent. We didn't get to that. Okay, so we were right here? Okay, so we didn't get as far as last period. All right, that's what I needed to know. So here we go. So have we talked about pph? We have not talked about pph. pph is just like finding your percent on a test. How do you find your percent on a test? What part you got out of the whole, right? And once you get that, what do? Times it by 100. So we also know this as percent, right? pph, parts per 100. Okay, to get ppm, we would multiply that number by 10 to the 6th, a million. Parts per million. And then ppb is another one they use a lot. We would multiply that by 10 to the 9th, which is a billion. So pp just means parts per, and then the bottom is whatever you times it by. So when we do a weight percent, we're using both weights. So we mass out the whole thing. We take the mass of whatever we're trying to find the percent of, divide it by the total mass, times it by 100, we got percent by weight. Weight by volume is if I take and maybe dissolve so many grams of salt into water. So I would take the grams divided by the volume that I dissolved it in, times 100. Volume to volume would be like I take two things that are liquid. For instance, we often use it at the grocery store, 3% hydrogen peroxide or rubbing alcohol. That's not all alcohol, that's water and alcohol mixed, and hydrogen peroxide and water mixed. So that's a volume percentage. We usually use a 3% volume or 3% volume to volume of hydrogen peroxide. So that's how you get that. So it just depends on what I'm doing. These are all basically pph, right? And that should be with small h, sorry. pp, I can't, there we go, pph. That's supposed to be two small p's. But it just tells us what it's doing. Now, they don't do weight by weight. They just do W, and percent. You need to know that means weight to weight. They do WV percent, and you know it's weight per volume. Or they do VV percent, and then we know it's volume to volume. Now the volumes have to be the same, the weights have to be the same. So they either both need to be kilograms, or both need to be grams, or both need to be milliliters, or both need to be liters. Okay? All right. I think that, okay, we have one example right here at the bottom, real quick we'll do. Calculate the concentration of weight per weight. I think I cut off half of it. Remember water density is 1 gram per 1 milliliter. What does the rest of it say here that I cut off? Okay, so basically if they want weight to weight, I know this because they just told me 1 gram is equal to 1 milliliter is equal to 100 grams, right? So when I do weight to weight percent, I've got to take the weight, 5.3, divided by 105.3. because I need the total mass on the bottom. Okay, then I would times it by 100 and I would get my answer. We usually report percent in 2 after the decimal. Okay, not hard, right? Pretty easy. Okay, so we go to the next page. We got some others that we need to do. They're doing here weight to weight. With water, I can use 1 gram per 1 milliliter, so I can really quickly set that up. I guess I put the 5.3 there. So this one would just be 7.5 grams divided by 555 plus 7.5 grams times 100. Okay, see how that works? Pretty easy. So this one right here, you're going to do a little bit different. It says this much was dissolved in enough water to make 100 milliliters. And then they gave me the density. Remember, density E is equal to mass divided by volume. Well, if I'm trying to find mass, then density times volume. Well, here's my volume. Here's my density. I just plug those in and get the mass. That's the total mass.
You just do 100 times 1.
So we'd end up with what? 120, right? Grams on the bottom, and we'd end up with 15 grams on the top. And these are 0.0 and point, so we have 3 sig figs. But we would still end up with percent, and we would label it weight. And a lot of times they put that in parentheses. Okay. All right, so volume, you do the same thing. Okay, so if they give me each volume, I've got to add the 2 volumes together to get the total volume for the bottom. Okay, so I'm not going to go through those. I'm going to let you do that. Consider the blood volume of an adult with a blood alcohol level of 0.5 volume to volume can cause a coma. I think I've got it at the top of, nope, I don't. Okay, let me scroll it down. Okay, what volume of pure ethyl alcohol, if consumed in 1 long drink and assumed to be absorbed completely into the blood, would result in the critical blood level? So we know the blood volume is total 5, right? Liters. So we're looking for X. We know that if we times that by 100, we get 0.50. So we would go backwards and end up timesing both sides by 5 and dividing both sides by 100. So the 5 here would go out and the 100 would go out. And so 0.5 times 5 divided by 100 would be X. Now I need to know that it needs to be less than 5, right? Liters. So if I end up with something above 5, I know I did something wrong, right? I don't have 5 liters in of blood, so if I've got more than 5 liters of ethyl alcohol, I'm in trouble. Yes?
So I got
0.25, and it would be liters. 0.0? There you go. So that's about 250 liters, milliliters. Okay. They probably don't want to come out right now. So that would be better. Okay, thanks. Okay. All right, so next we calculate the concentration, weight to volume. Same thing, okay? Just remember that the total needs to be on the bottom, okay? This time we would be wanting to find the milliliters for the solute, because it's not saying it brought it up to that. Let's just assume that this is solution. You guys are not going to need to do the other kind. So instead of water, let's just make it solution and don't worry about that. Okay, make it easier. Okay, so solution preparation. I'm going to go through this really, really fast. We're going to be able to do this again later when you're actually making up solutions. But basically, this is how you do. You figure out what molarity you want. From the molarity, how much volume you're going to use. So if I'm making 250 milliliters, I need to grab a 250 milliliter volumetric flask. And then I figure out how many grams I need to weigh out. I weigh the grams out. I got my thing here. So the first thing I do is weigh the grams out. Second thing is I put in about half amount of distilled water, half the amount to the line. Then I'm going to take and add my solid in here. That will be step 3. Then I do the shaky, shaky, shaky. That's step 4 until all of it dissolves. Then step 5 is I fill this up until the bottom of the meniscus hits the line on the volumetric flask. So my volumetric flask, the rest of it would be down here. Okay, so basically I've got 5 steps, right? And I know it says, I think there's 7. The first step would be figuring out what beaker size I need, how much do I need to weigh out. So those are the other 2 steps, okay? So let's go and do one. So here's one. I need to make a 250 milliliter. I need to make up 250 milliliters of 3.5 molar solution. Describe exactly how to do this. So I'm going to go step by step. So the first step is I'm going to grab a 250 milliliter volumetric flask, because I'm going to need that to make it. Second step is I know that molarity equals moles divided by liters. Well, I want to find out how many moles, so I'm going to take moles are equal to molarity times liters. Once I found out moles, I can take and really quickly take moles, and in 1 mole, figure out how many grams there are. So I can know how many grams I need to weigh out. Third step, weigh out the grams. Fourth step, fill volumetric flask. Half full with distilled water. Fourth, put in blank grams. I'm going to add to this and swirl to dissolve. Make it shorter steps. Step 6 here, add the H2O to the line. So fill it up till that bottom of that meniscus touches that line. And we're done. Now, of course, we'd swirl it a little bit more to get it mixed, but that's about it. Now, I didn't solve anything. I just told you how to do it. So how do I go about doing it? Describe. All right? Going forward. Move a little bit faster here. Okay, so dilution equation. This is, if you've had chemistry before, we've called it M1 V1 equals M2 V2. In your book now, it calls it C1 V1 equals C2 V2, because we don't always have molarity. Sometimes we have percent, sometimes we have parts per million, sometimes we have parts per 100. So we need to be able to do it another way. Remember that when we do strong acids, we always add the acid to the water. If you do it backwards, you end up having it splash back in your face, which is not a fun experience. Okay, so basically explain how we do this. I would just go and do it because it's easier to show mathematically how to do it. So as I go along, this is V1. This is C1. This is C2. And I want to find out what V2 is. Pretty easy. So rearranging the equation up above, we got V2 equals C1 V1 divided by C2. Plug in. C1 is 0.500 molar times 200.0 milliliters divided by 12.00, that's a 2. Molar cancels out, and I'll be left with milliliters. I can quickly find my answer by just plugging through. These are the same way. Percent, I can put in just the same as I did for any other concentration. It's just a plug and chug. Okay, the big thing is identifying what is what as you go through. Okay, keep things that are together, like these are together, so they need to stick together. So this would be V1, this would be C1. Okay, this would be C2, second concentration I came to. Again, you're solving for V2. Okay, going through the bottom one here, this would be V1. This one would be C1. This one would be C2. I'm looking for V2. Now, it's not always V2 you're looking for. Sometimes you're looking for C2. Okay? So, everybody okay with this? It's just plug and chug. Okay, moving on. Stoichiometry. This is where I have to stop at moles. I have to figure out how much of something I have in moles. So this one wants to know how many milliliters of this would I need to have exactly 20 grams of pure solid to react with 20 grams of pure solid NaOH. Well, if I was to do this, there's one H, there's one OH, so I know they're going to be a 1-to-1 ratio. And everything in here is a +1 or a -1, +1 or a -1. So if I wrote the equation, it would all have ones to balance it. Since I did that, I can really quickly say, okay, HCl plus NaOH yields NaCl plus H2O. Strong acid, strong base gives me water. It's balanced, nothing to do there. So I take first and I say, okay, I have 20 grams of NaOH. In 1 mole of NaOH, there are how many grams of NaOH? We'd have to add that up. Then, the next step would be to go to the equation because it wants milliliters. Well, I know in 1 mole of NaOH is needed for 1 mole of HCl. So when I get done here, I'm going to get moles of HCl. I also remember molarity is equal to moles divided by liters, and I have molarity over here. So I'm going to take molarity. I want to find my liters, so I'm going to take and rearrange this so it's moles divided by molarity. So once I get my mole here, I'm going to divide it by 6.00 molar. That will give me liters. They want it in milliliters. So in 1 liter, there's 1,000 milliliters. And I've got my answer. So it's nothing we haven't done already. It's just a matter of I've got to think it through and say, how can I get there? Okay? Now, in the second one, it's not a 1-to-1 ratio. So we've got to make sure that when we write the equation and balance it, because we want to do milliliters again, we've got molarity, but we've got BaOH2. We've got a volume, we've got molarity, but we've got HCl this time. Okay? So if we write this BaOH2 plus HCl is going to OI, outsides and insides, Ba plus 2, Cl minus 1, need 2 of them, plus insides of the OI, H2O. It's not balanced. Can you see it's not balanced? What do I need to do to balance it? 2 in front of the HCl, and then it's balanced, right? Oh no, what did I miss? 2 in front of the H2O, right? Right? Okay, 2 in front of the H2O. All right, so on this side over here, the ratio is 1 to 2. So I'm going to start the same way, except this time I'm going to use this equation right here. Whoops, not right there. I'm actually going to use this equation, but rearrange it for moles. So I'm going to go moles are equal to molarity times liters. And then I can change from moles of one thing to another. So I'm going to take 0.19 molar of HCl, and I'm going to times it by the 30.0 milliliters, but I got to change that to liters. So I'm going to divide it by 1,000 milliliters and put 1 milliliter here. And I'm going to get here moles of HCl. Everybody okay with that? All right, then I'm going to use my conversion here to convert. I'm going to, for every 2 moles of HCl, I need 1, or I get 1 mole of barium hydroxide. to balance it out. Okay, now I've got moles, right? Now I go back at the top because it wanted milliliters. Now I'm going to be using this equation right here to find liters. So now I'm going to take that mole and times it by, nope, not times it, divide, whoops, sorry, there went my 2. Divide it by 0.225 molar. That will give me liters. Do the same thing again, 1,000 milliliters divided by a liter, and I've got my answer. I need to fix that too for you. Sorry. Okay, you're going to do the same thing on number 3. I want you to have a chance to do it by yourself. Okay, so I'm leaving that one to do by yourself. Okay, solution of properties. We need to move fast or we're not going to make it to the lab. Electrolyte, non-electrolyte. Very simple. Electrolyte are ionic. They're going to split into particles. They're going to split into ions. So an electrolyte will carry a charge, will carry electricity. So electrolyte, ionic, splits into ions, carries a charge. If you haven't got that written down, write it. Non-electrolyte, covalent, bound, does not split into ions, does not carry any electricity. We had the 4 colligative properties. We worked with a couple already. Freezing point depression, boiling point elevation, osmosis is possible. We've done a lab on both freezing point and osmosis. We're going to finish the lab on osmosis today. And then vapor pressure lowering. That's the 4th one. So we have 4 things that are colligative properties. We've already used the equation for two of the colligative properties, which are freezing point depression. Delta T for freezing point is equal to K of freezing point times molality times I, or delta T for boiling point is equal to K of B times molarity times I. That's a KF, sorry. KF. Now remember that molality is equal to moles of solute divided by kilograms of solvent. So it's a little bit different than molarity. Molarity was moles of solute divided by liters of solution. Molality is moles of solute divided by kilograms of solvent. Now I is molality is moles, yeah, that's this molality. It's an italicized lowercase. That's molality. Now we're going to be able to use either a chart or you're going to be able to need to put on your cards these two, and this is 1.86. It's really hard to read. Degrees Celsius per molal. For water, we use that a lot. The Van Hoff factor is the I. It basically means how many parts will it break into. So if it's going to break into parts, it's got to be ionic or polar covalent. If it's not going to break into parts, it's going to be covalent, and the I will always be 1. So as I look at these, NaCl, far apart on the periodic table, ionic, there's 2, 1 Na plus and 1 Cl minus, so the I here is 2. Sodium sulfate breaks into 2 sodiums, 1 sulfate, so the I here is 3. Sugar is covalently bound. It won't break into ions, so it is a 1. Silicon oxide, silicon dioxide, look up here. Silicon and oxygen are closer together, so that's covalent, so it's going to be 1. Vanadium 5 oxide. Vanadium is in the middle and oxygen's over here, so it's going to be polar covalent. So I'm going to say, okay, vanadium is a +5 and there's 2 of them. Oxygen's a -2 and there's 5 of them. 5 plus 2 is 7, so its I is 7. Copper 1 oxide, 2 coppers, 1 oxygen, I is 3. Carbon tetrachloride. Carbon and chlorine are close together on the periodic table, both above the staircase, so it's going to be covalently bound. It's a 1. Barium and hydroxide. 1 barium, 2 hydroxides, I of 3. Charges don't matter. It's just how many parts are they going to break into. So like this one, magnesium phosphate. I have 3 magnesiums at +2. I have 2 phosphates at -3. The charge is balanced, but I have a total of 5 parts that they'll break into. 3 magnesiums and 2 phosphates. So it's going to be a 5.
So number 2 is 3 and not 6.
Because I end up getting 2 sulfates, 2 sodiums, and 1 sulfate. Hi.
I was wondering if you do labs in this lab.
Mm-hmm. In about 15 minutes.
Oh, really? Thank you.
Mm-hmm.
Is it okay if I come take pictures?
Mm-hmm.
Okay, great.
Mm-hmm. Okay, so going forward, calculate the freezing point. You just plug it into that equation. Delta T equals K of F or K of B times molality times I. Okay, so you just plug in. Now you got to be able to figure out what the I is. So what's the I on this first one in A? How many parts will it break into? 2 ammonia and 1 carbonate. So these are 2 polyatomics. They look like they're going to be a lot, but I only need 2 ammonias to go with 1 carbonate. So I look at the groups. The groups that hang together and have a charge, they still hang together. Okay, so they're not going to break up. Okay, so I have a 3. So here my I is 3. I'm going to plug in the KF for water. If I want the freezing point, I'm going to do 1.86. If I want the boiling point, I'm going to do 0.512 times the molality times the I. Freezing point, depression, I'm going to take it away from 0 for the freezing point of water. Boiling point, elevation, I'm going to add it to 100 for the new boiling point. Okay? So sometimes people, for the KF, for water, just like to put it in as this, because it's going to be taken away from 0. So it's going to be below 0, and that way I don't forget. You can't put it negative because we're going to take it away from 0, right? So if you take something away from 0, it's always going to end up negative. That just makes it easier.
So our M is going to be the 1.50.
Your M is going to be, yes, 1.50. Okay, so going down to osmotic pressure here. Osmotic pressure formula, sorry, this rolled up underneath it. Osmotic pressure is going back to PV equals nRT, perv nert. But what they do is they rearrange it so that P is equal to N divided by VRT. Well, this is molarity. So they say osmotic pressure, which is like a capital pi. Okay, it's straight. It doesn't have any curvies like the lowercase pi, is equal to molarity times R times T. Now T has to be in Kelvin. Remember, Kelvin's degrees Celsius plus 273.15. R is 0.0821 atmospheres times liters divided by mole times Kelvin. So here it just becomes a plug and chug. You just plug into that formula. So this is a lot, this unit is a lot of just plug and chug. Once you figure out what everything is, you just plug it into that formula that works for it. So here, calculate osmotic pressure. You're looking for the capital pi. You've got molarity. This is your temperature. R is a constant. Okay, so remember your temperature here, though, needs to add 273.15 plus the 25. Okay? Right. I am recording. Hopefully, if you get lost in, you can go back. First 2 again, same kind of thing. Calculate osmotic pressure. Colloid, this is what we're going to be talking about today. Colloids are particles in between solution particle size and suspension particle size. They stay in solution, but they're big enough that they can catch light. And so they get what's called a Tyndall effect when you put light through them. So it's like headlights in fog. Okay? You're going to experience it today. If you take a sample and you actually take and shine a light through, okay? If I only see the light here and here, it's a solution. If the light comes through and actually lights up the whole thing, it sort of glows, you've got a colloid or a suspension. If some stuff starts settling out or if things start to separate and you can see different lines, then you've got a suspension. Okay? So Tyndall effect is when it lights up the whole thing. Dispersing media is what I put it in, dispersed phase. You can sort of see over here what things are going on and what you can make and some examples of what's going on. Okay, emulsifying agents and stabilizing agents are put into things to stabilize them so that they don't fall out, so that suspension maybe stays a suspension instead of falling out, or colloid is more stable. A suspension we talked about is bigger particles than a colloid. Where does this all come into play with dialysis? Now, we started the lab last time with dialysis tubing. Dialysis basically takes blood out, puts it through a dialyser, which has an osmotic or a dialysis layer here that things can come out of, and it has fresh stuff going in. So the blood volume stays the same. They have to be really careful because of stenosis of going back and forth, which is sort of gross. Now, these examples 1 and 2, you're going to be able to answer more after you go back and finish the last part of the lab. So you can see, how do things move? Does it move from more concentrated to less concentrated, or does it move from less concentrated to more concentrated? You'll be able to answer those last questions. And then I just put some other pictures down at the bottom so that you can sort of see what's going on with dialysis, sort of cool stuff, because a lot of you said you were going into medical, so I just put some extra fun stuff with the dialysis and how it affects and what this goes into. Okay? Questions? Okay, this is lab now. We're going to go really fast with the lab. What you're going to do is I'm going to break you into the 1 group of 4 and 2 groups of 3. Okay, so first row, you're 1, you 3 are a group, and you 3 are a group for the second lab. For the lab that you did with your partner, you're going to do it after you do this lab. You're going to finish it up after this. So you're going to go back, and there are test tubes back there. Quickly fill up 5 test tubes with about the same amount of water. Okay? Now, you'll notice that there's a little bit of a discrepancy between what's on the left in number 4 and what's on the right. Okay? The table is what you're actually doing, but if you look at the one on the left, it tells you about how much to put in. Okay? So you're going to take a test tube, and for the group of 4, you're each going to take one and leave one of them as a sample. For groups of 3, everybody's going to take one person's going to have to take 2. So whoever finishes first does the last one. You take your test tube and say, I'm in charge of dirt. I go get dirt, I put it in. I don't shake it. I just look and see what it does. I observe it, I write it down. Then I shake it. Put my finger over or thumb over the top and shake it. These are all things that are household stuff. They're not going to kill you, not going to hurt you. Okay, so just shake it up really good. See what happens. Okay, then you're going to take a flashlight. You're going to shine it through. Does it give you the Tyndall effect? Remember the Tyndall effect? It's going to light the whole thing up. When you shine the light through, it's going to light the whole thing up. If it doesn't have the Tyndall effect, when I shine a light through, I can just see where the light started or where the light exited. I won't see it in the solution. Okay? You're going to write that down. You're going to decide, if I were to filter this, could I get something out of it? I probably can see if there's something falling down at the bottom, I probably could filter and get something out of it. If there's not something falling down at the bottom, probably couldn't. We're not going to actually filter it. I want you to say, yeah, I would be able to get stuff in the filter. And no, probably not. Then the next one over is, what is it? Is it a solution, a suspension, or a colloid? So solution, I can see through, have no Tyndall effect, nothing falling out. Colloid, I can see through, but when I put the light on, it does have a Tyndall effect. It does light up, but nothing's falling out. Suspension, Tyndall effect, and stuff falls out. Okay, so I've got to label those. Then at the very end, it's heterogeneous or homogeneous. Is it the same throughout? Homogeneous. It's not the same throughout. Heterogeneous. Second page is just some questions. If you were given a solution that did this, what would it be? If I did a solution that was this, what would it be? Okay? So very quick and easy to finish. Questions? Okay, last period only took about 5 minutes for this one, and about 5 minutes to finish up. You need a stamp for both, clean up, make sure you wash everything out. Go.
You need, like, goggles for this?
You need goggles. Aprons are your choice.